Let's now spend some time going over a few different solutions to address these various issues we raised when trying to decarbonize the grid. I want to start by talking about grid storage. Grid storage enables storing electricity at a particular time and utilizing it at a later time. There are many different types of storage that differ in their electrical capabilities and where they can be installed. For example, the most traditional type of storage that has existed for a while in the grid is pumped hydro, where we actually pump water from a lower reservoir to an upper reservoir. And as we release water from the upper reservoir to the lower reservoir, as it flows, um, it, it can power a hydro power generation turbines that then produce electrical power. The limitation of pump hydro is that it really depends on the geography, so it can only be installed in certain locations. Other storage systems that have existed in the United States, for example, compressed air storage or CAS, where energy is stored in the form of compressed air, and as that compressed air is released, it can produce power, and flywheels, which were not very popular, but there has been some existing flywheels. The most transformative technology in electricity storage today is the electrochemical battery storage. The most popular electrochemistry is lithium ion batteries. And one of the reasons why it's so popular is because this technology has been developed for your cell phone and computers. And so it's very cheap to manufacture it today. So there was a very fast evolution in terms of the scaling. Storage can be used in many different locations. In fact, it can be used anywhere in the grid, particularly if we talk about electrochemical battery storage, which is very portable. Storage can be used next to a generation station to support the smoothing of the power being produced by the generation. The best example is, for example, having battery storage together with a solar farm or a wind farm, in which case you could store the intermittent power and basically shape it much like a traditional generator would do. Battery storage could be used in a transmission network location, as shown here. And there, the main role would be to decongest the transmission line. So if you notice a particular transmission line is getting congested just on a few hours of the day, you could use storage to store power in other hours of the day, which is then released at the time of congestion, reducing the requirements on the transmission line. Storage can be used at the substation level, again, to primarily deal with flattening of the load, to handle the duck curve, for example. And storage can be used at a customer site, as shown here in the picture, where customers can store power when the electricity is cheap for them and then utilize it when the electricity is expensive. Or they can store power when their solar system is producing and they're not consuming and use it at a time of consumption in the evening, for example. So storage is very flexible. It can be used everywhere in the grid. Now, there are different applications that arise from these different uses. So as I mentioned before, storage together on the generation side can address a variety of issues. It can address supply disruptions, so a generator not being available. It can address the variability of renewable resources, or it can even provide peaking capacity. If you had a generator alone, to satisfy the demand shown in the picture, you would need to produce the curve represented by the sum of the blue plus the orange. But if you had storage, you could potentially store power at earlier hours in the day, maybe midnight to 6 a.m., and then utilize that power to reduce the peaks in orange. So that poses less of a challenge to the generators, ensuring they have a longer lifetime, or even that you could use cheaper generators. Storage can also be used together with renewables to address some of the variability issues. In this example shown here, storage is being used to patch up, the effects of clouds, for example. So you could store power and actually smoothen the fluctuation of the solar and renewables. On the transmission side, storage can be used to defer transmission upgrades, typically by allowing you to store power and, for example, relieve transmission congestion or ensure that the voltages are up. Or storage could even provide the grid ancillary services. So it could look at doing frequency regulation by storing or releasing power according to the local grid frequency. Finally, on the distribution side, several different applications. Storage can be used to minimize electricity costs for consumers or reduce demand charges. It can defer distribution upgrades by storing power at hours of low demand and releasing it in the hours of high demand. I can relieve the burden on the transformers. I look at the peak demand is reduced. Storage can also be used to provide backup power during outages, and finally support microgrids, which are customers that have solar PV, storage, electric vehicles. The storage can be used in support of these technologies to kind of reduce the fluctuations and the impact on the grid and reduce costs for the customers. The services the storage can provide will depend not just on the location, as we saw before, but also the capabilities of the different technologies. So on the panel on the left, you can see at which locations in the grid, starting at the transmission level, which is, denoted bulk or ISO, at a regional level, which is typically, at your transmission network bus or the customer buses, at the feeder level, that's at the substation and below, and the site, which is a customer level. And on the x-axis, you can see the speed the storage has to have. It has to be able to respond in milliseconds all the way to days and even potentially years. And depending on the combination of the speed of the storage and where it's installed, it can offer different capabilities. So for example, if you have a certain type of storage that can operate in an hourly mode within days and can sit at the customer site, then you can do demand charge reductions or manage the rate of electricity at different hours. If you have storage now that can go at the same hourly or minute scale, but now sits at the bulk system operation side, at the transmission network side, you can actually do energy arbitrage, which means store power when the marginal prices of electricity are low and release power when they are high in the wholesale market. Similarly, if you have storage that can respond in seconds, a very fast response, and they are installed at the bulk level, they could participate in frequency regulation markets, for example. Now, in the same way, if you have storage that can respond at the scale of years or a whole year, for example, by storing power as hydrogen and then using it later to generate power, then you could defer certain types of capacity upgrades. For example, you could handle the seasonality of renewables, the summer versus winter challenge. So those are all out here. And then on the right-hand side, we can see the response times of different types of storage technologies. For example, from this very nice paper from Cook et al., you can see that battery storage, is very good in responding up to hours. Um, Electrical fuels, different types of fuels. So for hydrogen, it can respond, up to years. You can even store it multiple years, not just over 1 year. Pumped hydro is very good at providing energy services in the scale of hour to days or weeks. And so the sweet spot for batteries is dealing with the very fast millisecond response all the way to a few hours. In fact, a reflection of this is in what the expectations are for the share of different services that different types of storage will have in the future. And you can see here in the first bar, we have pumped hydro storage, and about 90% of what it will be used for is electrical energy time shifting. Because that time shifting, you are shifting it in the wholesale market over hours, over a day, or even over one day to the next. In the same way, when you look at battery storage technology, it certainly 50% of it is expected to serve a frequency regulation. And then the rest is kind of distributed between electrical bill management, which is a customer behind the meter storage application, the ability to offer spinning reserves or real-time markets, which is another 10%, and electrical energy time shift, about 10% as well, renewable capacity firming, which is the ability to be right next to a wind or solar plant. That's about 5%, and then 20% is others. So it's a very different mix than for our pumped hydro service. And if you look at thermal storage, the ability to store power as heat, either underground or even in a HVAC, pre-cooling and other forms of heat storage. It's mostly utilized for renewable capacity firming and renewable energy time shift. Since battery storage is so important, I selected a few examples of existing sites just to show what's been happening in terms of the size of these systems and how effective they can be. One very famous example is the Hornsdale Power Reserve. This is a battery storage station in southern Australia. It is formed by a collection of Tesla Megapacks, as shown in the picture here. It has 100 megawatts of power that it can access at any time if you have energy stored, and it is able to store 129 megawatt hours of energy. The cost for this system was about $66 million when it was installed. That's $511 per kilowatt hours of energy stored. And just in the first year of operation, the regulation services netted this site $40 million. So they basically recouped the investment in less than 2 years. Another example of a storage station is the Peña Station in Colorado. This is an Xcel Energy system. And in this particular case, this is a station installed in support of a microgrid, but the storage is installed at the connection point of the distribution system, so at the substation. So the size of the system is smaller, is about a megawatt with 2 megawatt hours of energy capacity. It cost about $500 per kilowatt hour, and it has been used to basically support the solar in this local microgrid, which is a complex of office buildings. The last example is behind the meter storage, and here this is a deployment done in California. It's an LG Chem residential unit 10. It has 5 kilowatts of power capacity and 10 kilowatt hour of energy capacity. The cost is $500 per kilowatt hours with incentives, and it saves for this particular collection of homes on average $640 per year. has an 8.5 years of payback in a solar plus storage system. So you can see the different variety of applications and the sizes and costs. These costs are decreasing very quickly from the times we had these installations, and they are already nearly half of what these initial systems cost. Now, designing battery storages for the grid is something that has been challenging, and there's still various important issues that need to be addressed. First, we need to be able to address the issue of safety because we have a large numbers of lithium-ion batteries inside these storage systems, and they require advanced battery management systems and coordination for safety. For example, you have to do very careful thermal management because if you have a runaway heat event, batteries can catch fire. 23 of the 522 lithium-ion battery storage systems in Korea have caught fire since 2017, and this is really not very acceptable. Cost, because of the large number of battery cells or individual batteries that are used to form these storage systems, the cost can become quite high. In terms of performance, we need to be able to understand what is the purpose the battery system is being used for, how many times it is expected to cycle, will it cycle hourly or daily, and how to handle these high and low temperatures. And finally, the lifespan, meaning the ability to operate outdoors. These are existing technology challenges that we need to address to enable the expected large amount of battery storage in the grid that will help mitigate the variability of renewables.